Hi, I'm Akshaya from Georgetown University. I'm going to present the paper Distributed Measurement with Private Set Union Cardinality. It's a joint work with Ellis Fensky, Aaron Johnson, and Mike Usher. So the private set union cardinality problem, consider a case where we have, say, 5 nodes in a network, and it's a distributed network, and it has like private data sets. So for instance, D1, D2, D3 are all private data sets, and each of them have, say, few items. So D1 has items I2 and I3. So in this scenario, we would like to know how many unique items are there across this set of distributed private data sets. And for that, we have to find the cardinality of the union of all these data sets, D1 union D2 up to D5, which is the cardinality of the set I1, I2, I3 here, which is 3. And there are some requirements here. For instance, the input must stay private because inputs could be sensitive and cannot be leaked to untrusted parties or competitors. And only the output should be revealed, nothing else should be revealed. So why are we interested in this private set union cardinality problem? So the private set union cardinality problem has wide applications. For instance, in case of anonymity networks such as Tor, it's used to actually figure out how many unique users participate in Tor or how many unique destinations are visited. And also in case of structured overlay networks such as CORD, it is used to actually figure out how many unique clients are there in the network or how many unique lookups are there, and all these without revealing the client's identity. And another popular application would be the World Wide Web, where we would like to know the number of shared users across several websites. And all this we want to know without revealing anything about the user's identity. So now let us try to build solution for the private set union cardinality protocol. So this is a very nice solution. So there are N databases and they have data sets. So they just send these data sets to a trusted third party. The trusted third party just like computes the cardinality of the set union and it outputs the set union. However, this solution has a lot of drawbacks. So we will see the drawbacks. So as we already discussed, sensitive data cannot be leaked to competitors or untrusted third parties, and it's really hard to find a trusted third party in the real time. Next challenge would be the output itself can leak partial or complete information about the input. So let's suppose that the cardinality of D1 union D2 up to Dn is 1, and let's say that D1 has the item which is present in the union. In that case, D1 trivially learns the union from the cardinality of the set union, which is the output. So as we can see, the cardinality of the set union, the function itself does not like satisfy some privacy goals, but we want the output to satisfy some privacy goals. So just a background, now we are trying to actually use differential privacy to solve one of the challenges which we saw in the previous slide. So again, there are N databases. They send the data set to the trusted third party. And in this case, the trusted party, instead of just outputting the cardinality of the set union, it also outputs the cardinality of the set union plus noise, which is a random value. So here we have the differential privacy guarantee, which is that output is independent of the inclusion of any single input item. That is, for instance, if there is input 1, the presence or absence of input 1 does not affect the output. That is, output looks similar, like in all the cases, irrespective of whether an item is present or not present. So a background on Tor. Tor is an anonymity network. We will be focusing on Tor mostly throughout these slides, though it has wide application in other problems as well. We will be focusing on Tor. So Tor is an anonymity network used by millions of users, probably. Like our understanding of Tor's usage is very limited. This is because it's highly risky to actually conduct safe measurements on live Tor due to Tor's privacy goals. This is just a brief introduction to Tor. So there are clients, they would like to connect to the websites and they will want to do it anonymously. So there are a set of relays. The client connect to special relays called guards, which then connect to the middle nodes, which eventually connect to the exit nodes, which exit the traffic out of Tor to the website. So here actually the website does not learn the client IPs. So we would actually want to know how many client connects to Tor. And I would like to point out that our paper is not the first paper which has done safe measurements in Tor. There had already been existing research attempts on Tor, which actually do the study, like PrivX, PrivCount, and history. So these papers answer the query like how many clients connect to Tor, which we just saw in the previous slide. So here, the guards are going to have some privacy counters, like which doesn't reveal anything about what's inside the counters. We call them oblivious counters. So inside the oblivious counters, they are going to have the count of clients that have connected to them. So the first guard actually has 2 clients as the value inside its oblivious counter, and the second guard has one client as the value in its oblivious counter. And these systems actually give the output as 2 plus 1, 3, which is 3 plus some differentially private noise, so that the output does not leak any information about the input. However, these existing studies do not answer count distinct or the unique question. That is, we are more interested in how many unique clients connect to Tor. So in this example, it's slightly more complicated. For instance, if we see for guard number 1, there are 2 users connecting to it, which is like A and B. And I would like to point out that this is just a snapshot of Tor during a day or a week or a month. So actually, it's possible that users connect through different guards during different periods of time. So here for first guard, there are like 2 clients connecting to it. And for the second guard, there is just 1 user connecting to it. But here, since we want to know how many unique users are connecting to Tor, we would actually want the cardinality of the union, which is going to be the cardinality of the set AB. So the output we are expecting here is 2 plus differentially private noise. So performing such measurements like requires more additional goals. So let's now see what are the additional goals it requires. So the system should support multi-party, that is the relays are obviously like distributed. So the system should support multi-party computation. And the next one would be like malicious security. That is, since Tor is a volunteer operated network, the relays can behave maliciously. So the system should support malicious security. Then dishonest majority security. So actually majority of the relays, even if they are dishonest, they should not be able to reveal anything of an honest relay, any data of an honest relay. So another term which we coin is forward privacy. That is, forward privacy guarantees that like if at some point of a time a relay is compromised, the past data that the relay has collected should not be revealed at any cost. So that term we claim as forward privacy, and a measurement system should definitely possess this quality when it's going to be like deployed in live Tor network or some anonymity network. And this is the major goal which we have been seeing since slide 1. So the input should stay private. Here especially it could endanger an user's anonymity. So it's one of the major goals. And the output should be differentially private so that it does not reveal any information about an user's input or anything else. So there is no existing system that provides all these goals. So this is our paper, Private Set Union Cardinality. It provides solution for exactly this problem. So it provides the count of unique items in a distributed data set, and it provides strong privacy guarantees through differential privacy mechanism. And it's proved secure in the universally composable framework. This is a very important point because it allows private set union cardinality to be a component of a larger system. in real time without losing any of its security properties. Of course, the larger system should also be secure in the UC framework. And it incurs moderate overheads. So this is really a high overview of PSC, like abstract overview of PSC. So the private set union cardinality actually has three participants: the analysts, the data parties, and the computation parties. Analysts, at least initially, we envision it to be the maintenance of Tor, and the data parties are just going to be relays in the network. So in case of the example where we are counting the unique client IPs, it's going to be the guard nodes. And in case we are interested in the destination visits, then it's going to be the exit nodes. And computation parties are dedicated servers, which we introduce into the Tor, which are dedicated servers which is going to carry out which is going to execute this private set union cardinality protocol. So for example, the maintenance of Tor would like to know how many unique client IPs were observed in the last epoch. So the data parties do a data collection phase where they collect data using Oblivious Counters, and they pass it on to the computation parties. The computation parties execute a protocol phase, and they output the set union cardinality with differentially private noise, and then they send it over to the analysts. So security properties. No information from a non-SDP is ever exposed. That is, even when there are a lot of dishonest, as we saw, it supports dishonest majority security. So even when the majority of the participants, like the relays and the computation parties, are dishonest, honest information from a data party is never exposed. And it's tolerant to malicious computation parties and data parties, as long as at least one CP remains honest. And it does not provide integrity guarantees, in the sense that we already saw Tor is a volunteer operator network. So relays can act maliciously, so they can report junk data. And the computation parties can also disrupt protocol by adding excess noise. So the result we get may not be the private set union cardinality, which we expect it to be the actual private set union cardinality. But however, the privacy of an honest user will never be compromised. An honest data party will never be compromised. That's the major guarantee that private set union cardinality provides. So now we are going to focus on the data collection phase. That is, we are going to see how the data parties collect data obliviously. So we are considering the example, the number of unique client IPs observed in the last epoch. So here we have taken the example of IPv4, though it is applicable for IPv6 as well. So there are 2 power 32 IPs in the address space. This is a huge number of counters for any relay to handle. So actually we hash these IPs to integers in the range 0 to b minus 1, where b is much lesser than 2 power 32. Of course, this would incur some collisions, and this allows for some loss of accuracy. And so the DPs actually maintain a vector of B encrypted counters. All the entries are initialized to 0 in the beginning. So we will see now how actually it could be initialized to 0. So this is a data party. It has B counters. And let's say there are M computation parties. So the data party, for every counter, it shares a symmetric key with each of the computation party. And the data parties encrypt their counters with the symmetric keys shared with the computation parties. So actually here it just takes the summation of all these symmetric keys, and that's going to be interpreted as 0. So this is how each of the counter is initialized. And the counters are stored obliviously. That is, immediately after initialization, the DPs just discard their keys used for encryption. But even though they had discarded their keys, they would still be able to update the counters obliviously. So let's look into how the data parties are able to increment the counters obliviously. So here there is a relay. It has B encrypted counters, all initialized to 0. So let's say it observes an IP, IP8, it hashes it, and let's say it is hashed to the counter 1. So now it needs to increment the counter 1. So to increment a counter, the relay just adds random number r to that counter. So here we interpret non-zero values as encrypted ones. So with high probability, whenever it increments a counter with a random number, it's going to be a random number. Sorry, it's going to be a non-zero number. So non-zero values are interpreted to be 1. So far we have seen how the data parties actually collect data using oblivious counters, how they increment their counters obliviously. Now we are mostly going to concentrate on the protocol phase, which the computation party executes. So this is the actual computation of the private set union cardinality. So the protocol phase is divided into 6 substages. We will be looking into each of the substages in detail in the following slides. So let's focus on counter forwarding. So there are D data parties, and each of them is going to have B encrypted counters, which they have updated obliviously in the last epoch. And there are M computation parties. So each data party sends shares of its encrypted counters to each of the computation parties. So this step is mainly performed because even if m-1 of the computation parties collude, they will not be able to reveal the encrypted shares which the data parties had sent to them. So this guarantees that PSC is going to be secure as long as at least one computation party remains honest. So now let's see how the computation parties add differentially private noise. So there are M computation parties, and each computation parties are actually having B encrypted counters from each of the data parties because the data parties had done secret sharing scheme. And the computation parties actually map 0 values in those counters to the identity element in the algorithm group, and the non-zero values are mapped to a random element in the algorithm group. So this is just done by raising it to the power of the generator in the algorithm group. And once this is done, they just multiply all these shares, and each of the computation party just displays its output. So for displaying this output, they use authenticated broadcasts, the details of which you can see in the paper. This secure broadcast is like every computation party signs its message and like sends it over to every other computation party. So again, they multiply the results which they have obtained. So at this point, the final set of B counters which they have got is nothing but the set union. And here the computation parties actually add noise using a protocol which involves verifiable shuffle. It's pretty straightforward. Again, the details could be seen in the paper. So this differentially private noise, the number of noise counters is actually based on the Dwar-Ketel scheme, which is presented in iCalc 2006. And at the end of this step, so there is the original counters plus the noised counters. So far we have seen how the data parties send shares of their counters to the computation parties and how the computation parties add differentially private noise. So now the first computation party just has the output from the previous step. So it's going to obscure the position of the noised and the unnoised counters by performing a verifiable shuffle. We perform a verifiable shuffle because verifiable shuffle provides the guarantee that output is, anybody could verify that the output is a re-encryption and permutation of the input. So after the end of this step, we just have a completely a vector in which the noise and the actual vectors are completely obscured. So now let's go into the counter re-randomization phase. So there are M computation parties, and this is the output from the previous step. So re-randomization is performed by raising to a random exponent. So this actually, what happens here is when we raise to a random exponent, 0 values are still 0, but random values actually, like the 1 values become random because a random number raised to a random number will be some other random number. So this prevents an adversarial computation party or data party from trivially dragging a counter. So at the end of re-randomization phase, we just have a set of vectors which is like completely obfuscated. So far we have seen how the counters are forwarded by the data parties to the computation parties using secret sharing scheme, and how differentially private noise is added, and how the position of the counters is completely obscured, including the noise. And we also saw how to prevent tagging attack by using re-randomization. Now let's focus on counter decryption. So as we already saw, it uses algorithm encryption, which is a homomorphic encryption. Now each computation party removes its decryption layer by layer, and we have the plain text. So the final step is the aggregation, where we just get the private set union cardinality. So here we assume the computation party 1 is going to give the output, but it could be any computation party. So it just does the sum of all the counters which it had got from the previous step, and it just subtracts n by 2. Here, n by 2 term corrects for the expected amount of added noise for a binomial distribution. And this final output is sent back to the analyst. So protocol summary. So here, counter forwarding makes sure that the inputs are kept private from any subset of the computation parties. And noise addition makes the output differentially private and does not leak any information about the input. The counter shuffling obscures the position of all the counters, including the noise counters. And counter re-randomization actually prevents the tagging attack, which we saw in the previous slide. And counter decryption guarantees that all computation parties must decrypt to get the output. So even if one of the computation parties did not decrypt it, nothing about the inputs would be revealed. And counter aggregation, which just gives the final output. So evaluation. We implemented private set union cardinality in Go, and it's available for download. So the query we used for evaluation is what is the number of unique IPs as observed by the nodes in an anonymity network. And for this, we used a synthetic data set, which we simulated based on a single guard's view of the live Tor network. So we just performed experiments of PSC, and we evaluated the output, both computation and communication cost. So these are the parameters: the number of data parties, the number of counters, the number of computation parties, and the privacy parameter. So actually, the number of data parties is taken as 20. So currently, the number of guards in Tor is about 2,000. So we just assumed if 1% of the Tor network uses private set union cardinality, so that's how we got the number of data parties to be 20. And the number of counters, we have taken it to be 200,000. This is because from previous studies, we actually were expecting some 20,000 unique clients. And with collision, to get the output with no more than 10% error, we would require 200,000 counters. And the number of computation parties is 5. This is the current number of directory services that need to be actually taken down to compromise Tor. And for privacy values, like epsilon 0.3 is suggested by the Tor project. And delta value, we just took it to be a very small value based on the Orcatel, which is 10 power minus 12. And we performed all the experiments in a local area network. So we don't focus on network latency. And we used AMD missions, which is from 32 GB to 528 GB of RAM. And all these are single-threaded. So computation cost, we got the computation cost by varying the number of counters from 31,250 to 500,000 counters. And the time is nominal. We get about 2 hours, 18 minutes for 125,000 counters. And we call this nominal because for a measurement system, it's just going to be measuring all throughout the day. And we are going to get the output at the end of a day, week, or month. So this seems to be reasonable for that. And We varied the communication cost by, we obtained the communication cost by varying the number of counters from 100,000 to 500,000. And for a 24-hour long epoch, it was very reasonable. It was just 720 bytes per second for data parties, which are going to be small missions, but about 17.5 kilobytes per second for the computation parties, which are going to be like reasonably dedicated servers with high process powers. So, summary. Private set union cardinality provides a count of unique items in distributed data set. The output is differentially private, that is, it does not leak any information about the input. It's secure against an active adversary that controls all but one of the computation parties. And it provides forward privacy, which I would again like to remind, it's an important property because even when a relay is compromised, the past data that the relay has collected will not be revealed. And it's secure in the universally composable framework. And it incurs moderate overheads. The open source is available for download at safecounting.com. Thank you. No, actually, we use algomal encryption, which is a homomorphic encryption. Only the initial step uses symmetric key encryption. And we also thought about having secure multi-party computation with differential privacy. But in that case, it would actually require constructing gates for all of the noise and everything. But here, it's much more straightforward. We just know the number of noise vectors, and we just get it.
So, did you notice any hash collision when you did the hashing of the IPs?
Actually, there should be, because we tried to actually when we simulated it, we didn't map the IP address to the counters. What we did is we just had assigned the synthetic data set we got was we assigned values for the 200,000 counters and we just emulated the experiments. But when we deploy it in the live Tor network, definitely there would be collisions, because of which there would be loss of accuracy.
Nice. Thanks. And another question is, do you think how one should extend your, is there any possibility that your methodology will be extended for computing set intersections? Or is there any possibility?
Set intersection, actually, it could be maybe extended, but one of the drawbacks which I just think from the top of the mind would be it already reveals the cardinality of the union. So if you just want private set intersection or just private set intersection cardinality without revealing this, then it may not be directly extendable.
Thanks.